Okay, the last thing I want to talk about this lesson are z-scores. Now, one of the reasons the standard deviation is so important to statisticians is we tend to use it like you would a ruler or a yardstick. We use it as a way of measuring distances in terms of statistics. So much of the work we'll do this quarter involves measuring distance from the mean. The standard deviation tells us how the whole collection of values varies, so it's a natural ruler for comparing an individual value to a group. And that measurement, that number of standard deviations from the mean, is called the z-score. So if we let z be the number of standard deviations a value is from the mean, then we have this formula here, that z is the value minus the mean divided by the standard deviation. Now, this will be the most common formula you'll use this quarter, so if you don't quite get it now, hopefully you will before the end of the quarter. So suppose the mean is 180 and the standard deviation is 52. Find and interpret the z-score for a value of 200. Well, recall, the z-scores are values minus the mean divided by the standard deviation. So in this case, it would be 200 minus 180 divided by 52. In the calculator, I would use a parenthesis, so 200 minus 180 parentheses divide by 52. And you see we get a z-score of 0.385. That tells me a positive means it's above average. 200 is more than the average of 180. So we are 0.385 standard deviations above the mean. So the value is 0.385 standard deviations more than the mean. Suppose the mean is 28 and the standard deviation is 8. Find and interpret a z-score for a value of 10. Well, in this case, the value is 10, the mean is 28, standard deviation is 8. So my calculator, I'll start off with the value of 10 minus the mean of 28 in parentheses, divide by 8. And I see negative 2.25. So the z-score is negative 2.25. The negative is going to tell me that the z-score is below, well, the value is below average. 10 is a lot less than the mean of 28. So the value is 2.25 standard deviations less than the mean. So data values above the mean will have positive z-scores. So for example, the z-score of 0.385 tells us the data value is 0.385 standard deviations above the mean. Data values below the mean will have negative z-scores. So a z-score of negative 2.25 would mean 2.25 standard deviations below the mean. And generally speaking, the farther the z-score is from 0, whether positive or negative, the more unusual it is. So later on in the quarter, one way we'll be able to tell if we have an outlier is by looking at the z-score. Alright, back in 2014, Andrew Jacob Cervantes weighed 15 pounds 2 ounces when he was born by emergency cesarean section at Desert Valley Hospital in California, San Bernardino County. His impressive weight makes him a candidate for the state's largest baby and possibly one of the nation's biggest in recent memory. So assuming the mean male birth weight is 7.5 pounds with a standard deviation of 1.25 pounds, calculate the z-score. Well, let's first convert. 15 pounds 2 ounces is 15.125 pounds. So I take that value and subtract off the mean of 7.5, then divide by 1.25. Do it on my calculator. So his weight, 15.125 pounds, minus the average birth weight is 7.5, and then divide by the standard deviation of 1.25. We get a z-score of 6.1. Now, what does that mean? Well, generally speaking, z-scores are between negative 3 and positive 3. We really go beyond that. So what does a 6.1 mean? Well, to kind of give you some idea, variables such as birth weights tend to follow a predictable pattern, what's called a normal distribution, We'll talk about that more in a few weeks. In this distribution, a z-score of 6.1 is extremely rare. So z-score is more than 1. That occurs it's about a die roll, about 1 in 6. So not too unusual to have a z-score more than 1. A z-score more than 2 occurs about once in 44 attempts. A z-score of more than 3 is about once in 750 times. Z-score is more than 4 is about once in 32,000. A z-score more than 5 occurs about once in 3.5 million. And something more than 6 is about 1 in a billion. So extremely rare. Nice thing about z-scores, it allows us to compare observations in one group with those in another, even if the two groups are measured by different units under different conditions, such as inches and pounds. Or if you want to compare a student who took an ACT test to get into college versus an SAT test, for instance. So, for example, suppose we have two students who took the statistics final from two different teachers, and these two exams had different means and different standard deviations. So, one scored 82 on a test. They had a mean of 78.5 and a standard deviation of 2.3. Serena scored 58 on the test, had a mean of 40.2 and a standard deviation of 4.3. So, one scored higher, but then the average in his class was a lot higher as well. So, whether he was better relative to the rest of his class is not quite clear. His z-score, 82 minus the average, his value is 82 minus the 78.5 for his class average, divided by the 2.3 for the standard deviation. One scored about 1.52 standard deviations above the class average. Serena, on the other hand, 58 minus 48.2 divided by 4.3. Serena was 2.2 standard deviations above her class average. So technically, in terms of relative to their class, Serena had the better score. So, which student had the better exam relative to the respective classmates? I mean, one scored higher, but relative to the rest of the class, Serena was more impressive. All right. Finally, suppose that the mean is 18 and standard deviation is 5. Find the value that is one standard deviation above the mean. So the answer to that, we can start with the formula. We know the mean is 18, and standard deviation is 5. We don't know the value, but we know the z-score is 1. So what we can do is kind of rearrange the z-score. Value minus mean divided by standard deviation is the z-score. If you rearrange the pieces, then you can say that the mean plus the z-score times the standard deviation is equal to the value. So the value that is one standard deviation above the mean, well, if you go 18 plus 5, gives you a value of 23. Suppose the mean is 28 and standard deviation is 8. So find the value that is 2 standard deviations below the mean. So let's try this. I start off with a mean of 28. I want to be 2 standard deviations below the mean, so if I subtract 1 standard deviation, that puts me at 20. I subtract another standard deviation, I'm at 12. So the value must have been 28 minus 2 times 8, or 12. And finally, suppose the mean is 14.6 and the standard deviation is 2.1. So to find the values that are 1.96 standard deviations above and below the mean. So we start off 14.6. If I want to find the value that's above, I go 1.96 times the standard deviation of 2.1. That gives me a value of 18.716. Now, I can do the same thing, take this same calculation, except change that plus to a minus. Whoops, too far. Change that plus to a minus. And I can see that my 1.96 below the mean gives me a value of 10.5. So below the mean, 14.6 minus 1.96 times 2.1 equals 10.484. Above the mean, I add that 1.96 times 2.1 gives me 18.7.